Hello, I'm Yanakieva, and today I'm going to talk about our paper on the impossibility of confidentiality, integrity, and accessibility in highly available file systems. On this work, I've worked with Michael Yosef, Ahmad Hussein Rezai, and Annette Pianusa. First, let's start with introducing what distributed file systems are. They organize data in files and directories which form a hierarchical structure. This is depicted in the following picture. On top, we have the root directory, which can branch out into multiple directories. Each directory can contain further directories and/or files. Each entity can be uniquely identified, for example, via its path. If we take a look at the picture on the right again, the identifier of the bin folder could be, for example, root/bin, and then we know that this is unique. Distributed file systems also allow multiple users to work concurrently, and it is therefore important that they provide both high availability and security. We define security as consisting of confidentiality, integrity, and accessibility, which will be explained later in more detail. The common operations of a file system include modifications to the hierarchical structure by creating new files and directories or performing move operations on files and directories. File systems also allow content modifications of files and definition of security permissions for users and files. The latter is then based on an access control policy. Throughout our work, we have used the common POSIX access control policy, which includes three types of authorization: owner, group, and others. The owner of the file is allowed to make changes to the permission set for all authorization types for the specific file. By default, this is the user that created it. The group of the file is a set of users that have a specific type of access to the file. Others are all the other users that are neither the owner nor are contained in the files group. Furthermore, for each authorization type, a type of access permission is defined, which can be read, write, execute, a mixture of those three, or none. Based on this definition of distributed file systems, we can identify the following challenges. High availability, coupled with the fact that multiple users are allowed to work simultaneously on the file system, on the one hand predisposes concurrent modifications to its content and structure, and therefore a strategy needs to be designed to resolve such conflicts without losing data. On the other hand, incorrect merging of concurrent updates to the access control may lead to internal data leakage and corruption. We have identified that previous research on the topic focuses mainly on merging content and structure conflicts, but fails to provide a satisfying solution for merging conflicts on the metadata level, especially conflicts in regard to the access control. To visualize what we mean, imagine the following situation. We have our distributed file system with two replicas. Alice and Bob simultaneously work on it. Alice is connected to the left replica and Bob to the right one. On her side, Alice adds a file under the root directory called f.txt. At the same time, Bob adds a file under the root directory with the same name. If we were to keep both files unchanged, we would violate the unique identifier requirement. What is then the correct state that the file system should converge to? One good strategy would be to keep both files and rename them so that there is no identifier collision, as shown on the right side. Now imagine the next scenario. Again, we have our distributed file system with two replicas. Alice is working on the left replica and Bob on the right one. Alice is furthermore an administrator of the system, which means that she can change file ownership of any resource and resource permissions. And Bob is a user. A file root/f.txt exists with owner Bob and group permissions set to read only. Now Alice changes the group permissions to read and write on her replica, while Bob changes the group permissions to f.txt to none. What would be the correct state here? In our work, we set focus on such challenges that occur when concurrently editing access control related data. We have obtained an impossibility result that confidentiality, integrity, and accessibility cannot be achieved in a distributed file system. We have formulated the result in a theorem which proof is derived from the CAP theorem. We furthermore proposed a formal model of a simplified distributed file system that makes use of CRDTs. Before we explain the theorem, let's introduce the notions that we argue about. Assuming that there is a total order on no access control operations, authorized users possess read and or write permissions for the resource at the time of access. Subsequently, unauthorized users do not possess such permissions for the resource at the time of access. Following from that, confidentiality restrains unauthorized users from viewing the resource, meaning that the user that does not have read access to the resource cannot view it. Integrity protects resources from unauthorized modifications, which means that the user that does not have write access for the resource cannot modify it. And lastly, accessibility guarantees that authorized users will always succeed at accessing the file. And this is both for read and for write permissions. The theorem states that a partition-tolerant distributed file system that does not provide strong consistency cannot guarantee confidentiality, integrity, and accessibility at the same time. Let's start with the proof. For better understanding, let's first look at the following situation. There exist two replicas, replica 1 and replica 2, and two users, Alice and Bob. Alice's operations will be depicted in blue and Bob's operations in red. At the start, Alice is connected to replica 1 and Bob to replica 2. Alice creates file F, and therefore F's owner and only group member is Alice. The default other permissions are set to read and write. The creation of the file is replicated to replica 2, and the state for file F on replica 2 is updated as depicted in the green box. After that, a network partition occurs, and updates cannot be replicated between the partitions for a while. Still connected to replica 1, Alice sets the other permissions to none. Again, this change will not be replicated to replica 2 yet. After that, Alice goes offline. Once she's back online, she connects to replica 2 without knowing that she's connected to a different state. She writes to F thinking that Bob cannot see her changes because she has previously set the permissions applicable to Bob to none. Bob then tries to read and write to F, and he succeeds. Once the network is not partitioned anymore, the state of replica 1 is replicated to replica 2, and the other permissions for F are updated to none. This scenario breaks both confidentiality and integrity, as Bob had read and write access after his permissions had been taken away. In the following proof, we examine three cases. The general assumption is that network partitions split the system into two disjoint non-empty sets of nodes. In the first case, the system always responds with the latest local permission state and is therefore highly available. On the previous slide, we saw an example of such a system where both confidentiality and integrity were violated. A similar example can be used to show that also accessibility can be violated. In the second case, the system responds with the latest local permissions when the network is not partitioned, and with unsuccessful otherwise. Because when partitioned, each request would get an unsuccessful answer, no user will be able to access any resource. This preserves confidentiality and integrity, but not accessibility, as authorized users will also get their access denied. In the third case, the system is not guaranteed to respond to a request, therefore it does not provide availability. However, availability and accessibility are closely related. If an authorized user issues a request to access a resource and no resource is issued, the user's access will be restricted despite them having permissions. Following from that, a not available system cannot preserve accessibility. Following from these three possible cases, we conclude that confidentiality, integrity, and accessibility cannot be guaranteed in a distributed file system. Once we obtained the impossibility result, we were tempted to find out whether weaker notions of the three properties would suffice to keep data protected in a highly available distributed file system. Similar to as done with weak consistency, we established a causal order on the access control and data operations. Thus, we slightly changed the definition of authorization. A user is authorized if and only if there exist some access control operations that grant them access rights, and there exist no intermediate operations that have taken these away. Using the weaker notions, we designed a formal access control CRDT-based model of a simplified file system. It sets focus on access control operations such as creating users, groups, and files. changing file ownership, changing files group, modifying permissions, and reading of and writing to files. To formalize the model, we use Replis, which is a verification and testing tool with inbuilt support for CRDTs and causal order. We tested the model against two invariants, one for confidentiality and one for accessibility. The model, as well as the results obtained, can be found in our GitHub repository under the following link. In the beginning of our presentation, we posed the following question: how should the following conflict be resolved in order to preserve security? We had a distributed file system with two replicas and two users, Alice and Bob. Alice is working on the left replica and Bob on the right one. Alice is furthermore an administrator and Bob is a user. File root/f.text with owner Bob and group permissions set to read only exists. Alice changes the group permissions of the file to read and write, and Bob to none. In our model, we assume that administrators have justifiable reasons for modifying access control policies. Therefore, such a conflict will be resolved in favor of the administrator. In the current situation, Bob will remain the file owner and the group permissions will be updated to read and write. Evaluating the test results, we obtained two important insights. First, when designing secure distributed file systems, it is important to specify the expected state for all access control attributes in the same transaction. Otherwise, this might lead to write queues and unexpected results. To illustrate this, let's take a look at the following situation. We again have Alice as an administrator and Bob as a user. Bob is again the owner of the file f.text, and the others' permissions are set to none. On her replica, Alice changes the owner of f.text to Charlie and leaves the other permissions as none, such that Bob will not be able to observe Charlie's changes to the file. On his side, Bob changes the other permissions to read and write. Because the attributes do not directly conflict, the replicas will converge to the following state. The owner of root/f.text will be Charlie, and the other permissions will be read and write. This state is not desired because Bob now still has full access to the file. To explain our second result, imagine the following situation. Again, we have the distributed file system with Alice working on the left replica and Bob on the right one. This time, both Alice and Bob are administrators. The file root/f.text with owner Charlie and owner permissions set to read and write exists. On her replica, Alice changes owner permissions to write only, and on his replica, Bob changes them to read only. Because both Alice and Bob have equal rights as administrators, we cannot use their role to determine whose action should take precedence. We have identified, therefore, two possible strategies for this scenario. The system can either converge to the more restrictive permissions, in this case none, or to the less restrictive permissions, in this case read and write. The first case favors confidentiality and integrity but sacrifices accessibility, because neither read nor write access will be allowed, although at least one of those was desired. In the latter, confidentiality or integrity will be sacrificed in order to achieve accessibility. In our repository, we have placed two models that depict these two strategies. To summarize, we have identified that previous research on CRDT-based distributed file systems focuses on merging content-related conflicts and fails to sufficiently address conflicts on the metadata level. We obtained an impossibility result that states that confidentiality, integrity, and accessibility cannot be achieved in a distributed file system. We therefore weakened these notions and integrated them in a file system model that focuses on resolving access control conflicts and represents the access control policy using CRDTs. Thank you for watching, and we're looking forward to your questions.